So let's start the morning. And I'd like to now call upon Ryan Bruer, the co-founder of Half Climate Design, who would talk about sustainability and environmental benefits of mass timber. Ryan's work with the Half Research Studio at the University of Toronto catalyzed the city's conversation around embodied carbon. Ryan continues to lead training workshops and to accelerate life cycle assessment literacy and alignment of best practices across Ontario. Ryan.
Yeah, it's my honor to be presenting this morning on sustainability and the environmental benefits of mass timber. But we can't talk about that quite yet without first understanding the mass of timber. And I'll explain what I mean by this by using a short story about two famous architects, Sir Norman Foster and Buckminster Fuller. We're following a tour of the newly completed Sainsbury Centre in the UK. Bucky asks, "How much does your building weigh, Mr. Foster?" 2 weeks later, Foster responds with a detailed letter writing, "Dear Bucky, you asked me about the weight and volume of my building, which are as follows." He continues to list out each category with its weight indicated beside it, and this includes the mechanical, the structural, the interior systems and finishes. With a total building weight at the bottom is stated at around 5.7 million kilograms. However, that is not a true representation of all the weights generated by the building project. And Mr. Foster's math is partially incomplete because for every ton of aluminum used in the custom panelized facade system shown on the left, 2 tons of red mud and mining byproducts are left in countries like Guinea, Australia, Brazil, and China, who export the world's aluminum. So you can't understand the Sainsbury Centre in Norwich without understanding the Norsk Hydro tailings ponds off the banks of the Amazon in Brazil. These are the same building. They're the same project. So the same question should be asked of wood. What is the true mass of timber? I was fortunate, one of my first architectural jobs was a research position studying the Canadian timber industry. And I got to trace its lines across the landscape while zooming around Google Earth from the forest to the city. And there was a particular focus on the tools of harvest, methods, and machines. As interesting to me as the statistics of roundwood sales or pulpwood exports, or even the literature on sustainable forestry management that's enforced across Canada, was the way the tools of harvest adapted to the land and to the true dimensions of the tree, like these remarkable geometries of play with the radial cranes, which in a way are defined by the dimensions of the forest, the lengths and girths of the trees suitable for production. And as a designer, I was especially interested in how the history of forestry shows that wood products have generally been shaped by the conditions of harvest rather than the conditions of construction or the inspiration of a draftsperson. And I believe that this can be a great advantage over other industries. Trees have a way of embodying their life cycles, presenting the externalities and history through its rings and textures. As experts in life cycle assessment, the tree is kind of doing our job for us. It's visualizing its own environmental impacts where it removed carbon from the atmosphere to hold in its woody tissue until it inevitably falls to make room for growth beneath. And I'm borrowing this fantastic illustration from Gray Organchi architecture, a practice out of New Haven. This drawing illustrates how, unlike aluminum, wood has this opportunity to bring its full mass to our projects. Shown here is how each part of the tree can be used to meet the designs of our buildings. At Half, we've come to understand mass differently, to include the externalities. One of my first experiences in understanding the true mass of a building was with this 7-unit townhouse development built in Toronto, just north of here, designed by Bate Zorba Architects. And we've had this saying around the office recently that we should just make it our motto to meet your heroes regularly. And this was definitely one of those situations where we got to have conversations with Andrew, the architect, and those conversations illuminated some of the project constraints and decisions which informed some of these beautiful details and material choices. Because this is, after all, a timber project shown here. Each of the wood material types included on the study. I'll just take a second to kind of explain this. So on the left, you see the material as it was used in the building model. In the center is the combined volume of those materials. And then on the right is an illustration of the volume of carbon emissions that is produced when you use environmental data against the total mass. The treated range to green cladding, minimal mass, minimal carbon. This category includes all the softwood and hardwood lumber, such as the structural studs, flooring, decking, stairs, and it's the highest mass timber category in the project, but with relatively low emissions. The floor joist supported by LVL beams is the lowest mass category with the highest emissions in the wood category. And the OSB, the sheathing product, which shows that nearly twice the embodied carbon intensity of the lumber when compared to kilogram per kilogram. But interestingly, when you compare the total material volumes of the entire project, it shows that what I thought was a wood building is in fact a concrete or foam building, where even this simple foundation, no basement, just a parking structure, but at-grade parking structure, accounts for a majority of the upfront emissions. And the same is true for the insulation. Different products like the mineral wool, low density mineral wool with minimal impacts, fiberglass bat, the same. The XPS insulation below grade, where 2 cubic meters of the material account for almost 50 cubic meters of atmospheric carbon. And spray foam. During this project, I was shocked to see not just the quantity of foams and plastics and other oil-based products like asphalt roofing, but when you look at the environmental data, the significant impact of these products. And so why is that? Why are we doing this? Because documents like this, the Canadian Wood Frame House Construction Guide, tell us to do so. If you look inside this guide, you see the list of things that make up a Canadian home, and 11 of them are made of oil. It's what we're being instructed to do as builders and designers. This led me, as a part of some of my thesis work at the University of Toronto, to survey the history of insulation in Canada. And what you find when you look beyond the past 100 years is that insulation and airtightness in buildings had previously been accomplished through natural materials. And I'm convinced that the green buildings of the future look probably more like the ones of history than the ones we're building today, built with stone, earth, wood, and vegetable fibers. Then on the right, a more recent history shows that the products of insulation are dominated by oil and gas industry. Let's look closer at an example like cellulose, which, come talk to me about this over the next 2 days, because this may be a hot take, but is cellulose also a mass timber product? It may not have been produced by a sawmill, but it was definitely one produced by a pulp mill. But when we look at the history of cellulose, it's greatly diminished from where it was in the 70s, when it was rapidly growing in popularity, pushed out by the utopian promise of foam as the perfect plastic building material. Supported by strong lobbying efforts, there are still many states in the US where some of the most harmful, the highest carbon emission global gas foams are still unregulated. And why is this? It's what we're being told. If you Google either cellulose insulation or XPS insulation, Google returns your query with diametric question prompts. On the left here, you see for cellulose, and on the right, you see for XPS, where for cellulose, it's generally negative connotations, and the right is positive. For example, is cellulose bad for the environment? Which is a bit of an absurd question. And on the right, why XPS is the best? An equally absurd question. HAF recently looked at available insulation products, plotted them against embodied carbon along the x-axis and cost in dollars per meter squared RSI in the y. And while it's not always an easy specification substitution, we have become accustomed to using materials which are not the lowest embodied carbon options and which in some cases are not even the lowest cost options. So this is the types of insulations we use in the GTA. The highest carbon foam products dominate with over 50% of market share, with our mass timber friend, cellulose, closer to 3%. Our insulation manufacturing is mostly local, although some products come from Quebec, primarily the XPS products. But in an area of the world as bountiful as Southern Ontario, I can't help but feel surprised by the lack of locally produced bio-based insulations. And I do a lot of long distance riding in this area. It's a part of the world I love very deeply. And it just makes me rethink how I can be a part of change to low carbon, locally sourced building materials from this area. And so this is why we founded HAF. As experts in life cycle assessment and the circular economy, we're aiming to halve the emissions of the built environment this decade by working with designers, builders, and policymakers. This instinct, of course, was motivated by early IPCC reports, which indicated that global greenhouse gas emissions needed to be reduced by 50% in order to limit warming to 1.5 degrees Celsius. 50% of what? For buildings, this includes the operational emissions and the embodied material emissions. This graph is a common one, which I would think you've seen. But if you were to redraw this graph for Toronto, that 39% impact from buildings grows to 61% of the city's total greenhouse gas emissions. Where we'd previously been designing to optimize operational energy use, we now need to design for this, the entire cradle to grave, and consider whole life carbon. So how do we do this here? Led by Kelly Doran, the HAF Research Studio began at the University of Toronto to ask this question: how do we halve the embodied carbon of all construction in Canada this decade? To date, there have been 3 years of students trained in life cycle assessment to ask this question. We completed the first upfront embodied carbon benchmark of residential buildings in Toronto, taking this group of 10 projects, which range from low-rise, mid-rise to high-rise across Toronto. Another year, we looked at the university campus, assessing some of the newer buildings constructed, and the goal was to assess not just the embodied carbon, but the operational carbon simultaneously using the operational data provided by the university. We also looked in another year at mass timber buildings. Are they as low carbon as they claimed? And of the 10 projects here, 4 of them are in Toronto, 2 are on the West Coast, and 4 were European projects from the UK and Sweden. The methodology was pretty simple. We took the projects, we chose a representative section of the building, modeled it in detail to quantify the materials, and then using environmental data, you can get results of the impacts. So here's all those buildings across the 3 years of the HAF Research Studio. So this is the upfront embodied carbon emissions, upfront embodied carbon intensity, I should say. For the residential projects, the results were fairly linear from low to high rise. Commercial and institutional projects are programmatically more material intense, and so there's just going to be an inherent higher carbon intensity for these projects. But what you see with the mass timber projects is that they are significantly lower than the U of T buildings. Although the goal was to train students, it was also about reaching out to the industry, partnering with the designers that were in some cases working on these buildings actively to start conversations. And education is core to the work we do at HAF and continues to be. This year, we've led seminars and workshops about life cycle assessment training with both the Toronto Society of Architects and the Ontario Association of Architects. So what's driving these emissions? Our buildings are icebergs. Foundations, basement parking structures, and below-grade floor area have disproportionate impacts on the project's embodied carbon. So let's go back to our timber townhouse. 66% of the embodied carbon emissions in that townhouse were below grade. So that's including the concrete, the membranes, insulation, damp proofing. The same was for the other low-rise projects. In one case, 90%, where there was a one-story below-grade parking area. So for a project that I wanted to consider a timber project from an embodied carbon perspective, this is a basement with a stick frame, much like the majority of Canada's housing. Looking at the mid-rise and high-rise buildings, the results were the same, ranging between 20 to 45, 50% of the emissions of multi-unit residential buildings is underground. The only exception here is 3 from the left, 22 Trolley Crescent, which because of soil contamination and groundwater restrictions, they weren't able to go below grade, which turned out to be a big benefit for them. The problem gets stacked with going below grade when you need to transfer the structural loads to accommodate different program. Parking and residential units is a classic problem in the city of Toronto, which has been primarily solved using transfer slabs and transfer beams. Uncommon in other parts of the area, this is a huge impact to the embodied carbon of our projects. And just because a building structure is mass timber doesn't necessarily mean it's low carbon. The iceberg scenario can still apply. Like the Adidas headquarters project, this really sophisticated hybrid system of precast concrete and mass timber, the same scenario was happening with more than half the emissions found below ground. Kind of the dividing line there is above, and you can see a 5-story below grade parking. 2, use less metal. Aluminum extrusion-based glazing and facade systems carry the highest embodied GWP by volume of all building materials. What should be here is like a food pyramid, but imagine a building materials pyramid where the top of the pyramid is the highest emitting materials and the bottom is the lowest. The lowest having natural fiber, wood products, and the highest having metals like aluminum and copper at the very top. And when we design our facades, we're generally picking from that top of the food pyramid. If the top is like your Wagyu beef, we're designing our facades with Wagyu beef every single time. Curtain wall systems, window wall systems, top hat, metal panel, aluminum panel, rain screen. When you look at just the upfront carbon, the facade only accounts for 10 to 20% of the project's emissions. Not too significant. But if you consider the whole life, the use phases like the B and C in life cycle assessment, the use phases and the end of life phases, that impact increases to 37 here or 40%. So it's really important to consider when you're thinking about the whole life of the building because of the replacement and repair. We've also studied embodied carbon side by side with R value. What is the trade-off with those two performance criteria? Here's a quick snapshot of kind of, you have low-rise, mid, and multi-unit design here, where on the right, the window wall systems are not only the highest emitting systems, but they're also the lowest thermally performing. In the mass timber study, we got to see some amazing envelope systems, which arguably were climate positive. A high amount of biogenic and bio-based materials like cedar cladding can perform the same way as other opaque systems, but not have the high embodied carbon. They can also look pretty good. Geography really matters. The grids our material sourcing and fabrication sit upon drives upfront emissions, while the grids our buildings sit on drive operational emissions. back to the townhouses, but looking instead at brick. The project had a fairly refined and rich design for the brick cladding. They couldn't find the right brick locally, so they had to search a little farther around North America. So the two types of brick came from Nebraska and Arkansas. Pretty far distances. You might think, well, that's the emissions there, all the diesel to get it to site. But in this case, it actually wasn't the transportation distance that was playing the biggest impact to the embodied carbon, but it was this electricity map, which illustrates that these bricks were fired using different electricity. Electricity in the case of Arkansas that is fueled by coal, and in Ontario, electricity fueled by nuclear or hydro. Distance can have an impact though, and we saw that with these three mass timber projects. The first, the Catalyst building in Spokane, designed by Michael Green Architects, U of T's very own academic wood tower, collaboration between MGMA and Paco Architects, and the Adidas headquarters in Portland by Lever Architecture, supplied by 4 suppliers of mass timber products, who again were supplied by 5 different lumber mills from Alberta, BC, Washington State, and Oregon. Those are those lines tracing out into the landscape where our materials come from. And the impacts were actually quite telling. The difference between continentally sourced lumber and locally sourced here was a difference of close to 7%. What's being shown is the percentage of total timber GWP. So just looking at the timber product, what portion of that was attributed to the transportation distance. So for the wood tower, it was 10.9, for the Catalyst building, 7.1, and for the Adidas headquarters, which was able to source local timber, it was only 2.7%. And a closer look at the life cycle assessment data of the Catalyst building, again, revealed why geography matters. The building used mass timber products from 3 suppliers, and here the 5-ply CLT floor, the largest volume of those materials, which is to be expected. The results of the half's LCA were 357 kilograms of CO2 equivalent per meter squared. However, the student was surprised to see that this result was actually significantly higher than an LCA completed on the same building by the University of Washington a couple years prior, which came out at 207. What could be the case for the discrepancy of looking at the same building? And a close reading of the environmental data that was used is that the University of Washington LCA primarily used industry-wide or generic environmental data. So that's data across a number of manufacturers or a larger region, whereas perhaps because the project had developed further, the HAF studio is able to use product-specific data. This is using like an environmental product declaration from a specific manufacturer about specific products. It's a much more accurate representation. So where wood comes from does matter. Does it travel a great distance to get to site? And what electricity was used to produce it? 4, and this is the last one, take a whole life view of carbon. Only by looking at both the embodied and operational carbon over the life of a project can we begin to make holistic decisions about carbon reduction. So here are 2 very similar buildings. In a way, they're both designed by Starchitects. They're concrete frame, clad in aluminum residential buildings. One is in Calgary on the left by Bjarke Ingels, and on the right, you have the Frank Gehry Towers in Toronto. But when you consider the city they're in and the region they're in, they actually need to be designed quite differently. For Calgary, because the operational emissions will be so significant, powered by the burning of fossil fuels, over time, the emissions of the operations of a building will eclipse the embodied carbon emissions of a building. But that's not the case for Toronto, where because the operational emissions are lower, the hydro, solar, nuclear power, that those operational emissions will and in this case, it gives you the kind of 2030, 2050 marks. They never eclipses the embodied carbon of a building. We took a look at this more closely, looking at the envelope. With Ted Kessick at the University of Toronto, we took 4 wall assemblies, 2 on the left residential and 2 on the right mass timber. We broke out the different material quantities within the assemblies and got results for their environmental impacts. You see aluminum, PVC, glass are the kind of big offenders, where in some cases the timber products are small slivers in the stack. And we then added the operational carbon to that embodied carbon to get a graph like this, where over time what you see is the slow increase of emissions from the operational use of the building, and marked intermittently by jogs of repair and replacement. So we can do this here. At HAF, we took the research at the HAF Research Studio and we approached the city. We got funding to do a policy primer to inform policy that would regulate the embodied emissions of buildings. We kind of took a case study with them, an EMS station being designed by Diamond Schmidt Architects, a CLT structure system, and we did a life cycle assessment. It was in late stage of design, and the opportunity was to make some specification changes that would reduce the overall embodied carbon intensity. So we identified some of the key material categories. We proposed alternatives that would reduce the overall emissions. And in this case, the top 3 recommendations we made were accepted and have been implemented in the building, resulting in a reduction of 800 tons of avoided emissions. I'm excited to say that as of a couple months ago, revisions to the Toronto Green Standard have been adopted that include, for the first time for a city in North America, absolute embodied carbon targets for city-owned buildings and for Tier 2 buildings. We're continuing our work with the city. We're now looking at the urban design guidelines, asking the question, are there unintended consequences to these guidelines on the embodied carbon of structures and buildings? Looking first, we kind of intro to that was looking at the step backs, understanding the different zones of a typical mid-rise construction that is, one would say, at the mercy of the angular plane, and proposing that a move to simplicity could reduce the embodied carbon of these structures. It would also move to a wider range of structural systems, and I think the encapsulated 12-story mass timber was definitely on the front of our minds, considering how urban design guidelines could make way for more of that construction in Toronto. And finally, this is something we're exploring with the Mass Timber Institute out of the University of Toronto, Intuitive, and Bird. Unfortunately, the report is not complete yet, but definitely keep an eye out, because we will be releasing a study which is going to be an embodied carbon and costing study for a archetypal office building, a 12-story office building, where we have Intuitive has designed 4 versions, 4 structural systems: concrete, steel, it says timber, but it's braced with no structural concrete core, and then the hybrid has a structural core with some steel members also. And we're going to have each of those 4 designs in 3 cities across Canada. So we're going to get cost and carbon from 4 systems in Toronto, Calgary, and Vancouver. And as a bit of a sneak peek, this is showing the embodied carbon intensity of just the structure only for this building in the city of Toronto, and the results are pretty telling, where I think it's clear which kind of structural systems we need to be prioritizing. Finally, a thought on the term mass timber, and then a question. That's the last thing. Terms are powerful. They can generate fields of exploration, but they can also limit scope. So my question is, can our understanding of mass timber expand to ensure diverse and sustainable forests accelerate all bio-based materials and generate the exploration of lower carbon emissions for all building materials? Thank you very much.
Ryan, thanks so much. That's amazing work that you're doing at the HAF Studio, and I hope we get to collaborate between George Brown and U of T, because you're doing amazing things. Thanks.
Thank you. Great.
Q&A now.
So we have opportunity for Q&A. So questions for Ryan?
Yes.
Just a question about the operational carbon. You sort of put it into the tutoring work with people. Did you take into account maybe using sort of developments and improvements in producing energy over time? Because that would hopefully improve as well. Let's make your case strong.
Absolutely. It's exactly. And when you electrify a building, it makes that case even stronger again. The operational emissions question is one with a lot of variability. So we are trying to work with people who are even more knowledgeable on that side of things, because there are a lot of assumptions you need to make. So it's not an exact science, but you're kind of taking your best guess exactly what the direction is for that from. Yeah.
Do you have any, like, when you look at that life cycle analysis? Hi there. When you look at that life cycle analysis that was done on the Katera building and how, what it was like 207 versus 357. So there's that vast discrepancy, which is obviously very much dependent on the lack of true EPDs and just kind of gathering general information. Do you have any data on, number one, manufacturers actually stepping up, and like, or is there any data on like just how many people have these available? And then secondly, any data on architects and designers making this a mandate for when they actually design and choose materials?
Yeah, great question.
That would help your job.
Yeah, absolutely. And so the first question, what is available out there? Thank you. It kind of ranges between product types. Some products, there's a lot of data out there. Concrete, there's an EPD for every mix type and every plant across Canada, it seems like. But for other products, thinking of like Division 7 membranes, there's not a lot of stuff out there. You've got maybe one or two to choose from. And in which case, the LCA starts to make a lot of assumptions about equivalency of these products. So, and then the next part of your question was, how can designers encourage or require this data from manufacturers? And that is another thing we're working with. We're working with a couple architects in Toronto right now to review their specifications, their master spec, to ask that question. And it's tricky, and I'm not an expert in specification writing, so we're working with people that know more, but we're trying to refine the language to motivate, at the very least, contractors being required to kind of query for that data to be included in submittals and things like that. So, to your question, I think what you can do is you can look for products that have that data, and then where there's not, you can ask. And then, I think that's going to build the momentum of getting manufacturers on board to provide that. Any other?
Better on operational.
Yeah, and I can bring that one up, but actually I know exactly the one you're talking about, and it's a bit deceptive of a slide because the scale, the kind of y-axis scale is different from one graph to the other. So what you were seeing is the same embodied carbon for both Calgary and Toronto, but they changed the scale of the graph to just show that minimal operational emissions for Toronto. It's not there anymore, but I can show it to you after if you want. It's it's one of those, when you're flying through it, it's a bit it's not clear, but in that case, it was the same embodied for Toronto and Calgary. Any other questions? Oh, yeah.
Thank you for the presentation. I was wondering about your opinions on how lifestyle and individual behavior would affect after the life starts within these buildings. So, yes, that's great to know and improve our design and everything up to a point, which is great, and it will improve a lot. But as far as we know, in the literature and applied science, there is also an argument, a real discussion on the lifestyle differences would affect the life cycle analysis, as well as not on at the building scale, but also at the neighborhood scale. So what do you think about these, and how do you think that future will be shaped in different lifestyles? Thank you.
Yeah, I think when it comes to whole carbon assessment, the circle starts to get pretty big of people that can be included that impact that building, and what I believe you're referring to is users as well as operators of the building. If the user's not educated, and primarily on the operational emissions side, that can have a huge difference, right? If you're running you got your windows open and you're running your heat pump 24/7, it's that can be a huge. So education definitely needs to happen there. And then on the operator side is the exact same thing. Not just the design of some of these systems, but with the work we did with the University of Toronto, we found that in almost every case, the energy models underestimated the actual use and emissions within each of the buildings, which we think of as an opportunity to learn from the experts of energy modeling and operational energy use. That what can we learn from them to make some of these assumptions more true throughout the life of the building. Any other questions? Okay, I think that's it then. Thank you very much, everyone.
Thanks.